a sound source will affect the frequency heard by an observer? Answer is C. Speed of the source relative to the observer. Okay, Doppler effect, classic. What ultimately determines the speed of a particular wave? This is a tough one. I know people are thinking V is equal to lambda F, but what we've said previously is that speed under the conditions that you're in is going to be a fixed value. All that means is that the speed stays the same. If the wavelength goes up, then the frequency goes down, right? To preserve that V value. So it isn't the frequency that makes things go faster, because that would just make the wavelength go down. The wavelength, no, that's the same issue. It's not the amplitude, because that's not about wavelength or frequency or anything. That's just about how loud. And if I could make things go faster just by shouting at people, I would shout more, you know? Yeah, exactly. Listen up. Let's get this done. Period. Well, that's just the reciprocal of the frequency, so that can't be it. No. Listen, it actually turns out it's the medium itself. If you got it, it turns out that sound travels at a different speed underwater than in air. It's the medium. All right. Number 4. What dictates the frequency of sound waves in air? Well, it actually...
sound in air.
It's C. It's the frequency of the source. Yeah. What changes the frequency? The thing that's making the sound. All right. And if you're dipping your finger in water faster and faster, that causes the period of the spreading waves to decrease. Yeah, faster and faster. Yep.
I think the answer to 4, what dictates the frequency of sound waves in air is D, the speed of it.
Oh, okay. All right. Let's talk about this idea of beats. No, beats. All right, so the idea of beats. So beats is the idea that if I make a sound and while there's a second sound being made at the same time, then those two sounds can overlap with each other. So if a tuning fork makes these longitudinal waves, that's great. But if I have two tuning forks and they both make longitudinal waves at the same time, then the peaks of one wave and the troughs of the other are going to interfere with each other to be destructive. We saw that with our demonstration with a slinky earlier. Destructive interference, right? That's why I did that thing with the slinky. Okay. Meanwhile, if I have two peaks happening at the same space, you get constructive interference. And what this means is that you're going to end up getting a loudness that happens. Now, if I think about that idea of superposition, two different waves, frequency 1 and frequency 2 happening at the same time, sometimes they're going to overlap to cancel each other out. Sometimes they're going to overlap to build each other up. And so these two frequencies being played at the same time cause this sort of like loudness and quietness fluctuation. And what it actually sounds like is more like wom, 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 loud, quiet, loud, quiet, loud, quiet. And so it's hard for me to really do that justice with my voice. So I'll try and pull this over. Shh. If I got these two different waves, whoa, wow. These two different waves are going past each other. Yeah, but they're overlapping with each other sometimes to cause constructive interference and sometimes destructive interference. This is my nicest, cute little animation for showing this in live action, okay? Because I can't show sound very effectively. This is a tough one. Show waves superimposed? Sure. Oh, I don't know what 2 means. Let's see what happens if I change it to 5. What if I change it to 0.5? Ooh, look at that. What if I change this one to 0.3? That's looking kind of ugly. How about we change it to 1? But can you see that there's like quiet spots and loud spots? And it sounds like wom, wom. It's almost like a throbbing sound. So that throbbing frequency, that wom, wom, wom. Let's get rid of this. Is what we're illustrating here. And let's just call it the wubba wubba frequency. Wom, 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 wubba wubba. That wubba wubba frequency, of course, that never caught on as a technical term, so we just call it the beat frequency. The frequency at which that throbbing happens, that whoom, whoom, whoom of the superposition, okay? Beat frequency. The math is not hard. If I have a sound source that has a frequency of 262 hertz and another sound source that's 266 hertz, what's the beat frequency going to be? You guys could do this in your head. What's it going to be? 4 hertz. Yeah, look at this. Beats is equal to F2 minus F1, absolute value, so it doesn't matter which one's the big one. 262 hertz minus 266 hertz, 4 hertz. This little illustration up here, same idea, F2 minus F1. This illustration had 128 hertz, absolute values, minus 512 hertz, 384 hertz. Okay? So I wouldn't even call the math on this one tricky. So let's move on to something else. I got another quiz thing. Oh, yes, sir.
Is that the same thing as F1 minus F2?
Yes. Yeah. Because it's the absolute value, so it doesn't matter, right? All right, so a skipper on a boat notices, a skipper, by the way, is that's a job on a boat. It's not somebody who throws stones. So skippers on boats should not throw stones. A skipper on a boat notices wave crests passing his anchor chain every 5 seconds. If the wave crests are 15 meters apart, okay, so we got a delta T of 5 seconds. Oh, this feels like a throwback to a previous topic. And the wave crests are 15 meters apart. That means lambda is 15 meters. What's the speed of the wave? Anybody do this one? Oh, so that's not just delta T, that's period. Okay, so we've identified wavelength and we've identified period. I don't even know if we need frequency, because isn't speed just equal to lambda over period? I know it's also equal to, speed is also equal to lambda times frequency, but in this case we're told the lambda and the period. I don't think I need to calculate the frequency. The wavelength is 15 divided by 5, well, that's 3. Fantastic. And again, I've had some requests around this point in the course where people always say, like, oh, could we do a little more practice with multiple choice? This is the kind of thing that you need to be able to do. Identify variables, especially for these calculation-based ones. Now, for a non-calculation-based one, for a medium transmitting a longitudinal wave, take note of vocabulary words. Longitudinal wave. The areas of the medium where the density in the medium is temporarily increased. All right, so remember, longitudinal wave, cue into the vocabulary. If an illustration helps, always add an illustration. Where the density is increased, we're talking about these guys here. Anybody remember what they're called? Compressions. So again, good practice. Underline your vocab words, draw pictures when necessary, choose the best answer. Now the other thing is, you can also, wait a minute, did I answer wrong? What's the answer? There's a good point. Last time I marked a multiple choice test, somebody said, oh, I meant to say B. I don't know that. I'm not your counselor. I don't know what's going on inside your head, right? Like, you got to circle the right thing. So make sure you proofread is what I'm trying to say, okay? Proofread your stuff. Density holes, that's clearly nonsense. I never heard of a density hole before, so play the game of elimination too. If you see nonsense, at least if you didn't know the answer, I could have eliminated that one as the dumb answer. And usually with multiple choice, there's at least a couple dumb ones, right? You can just eliminate. And then at least you got a 50-50 shot if you kind of know what you're doing. Okay. Let's take a look at the next page. Oh, before we do though, I gotta show you this website that I think is pretty. Oh, not this one. This isn't the one I like. This is the one I want to show. This idea of beats and superpositions. I actually kind of like this one. This one is actually about Fourier analysis, but it illustrates their idea. Look, I got two waves here. Right now they're identical because there's only one note being played. If I play a second note, ooh, see the superpositions on the bottom? I'm going to bring that back down again. Oh. But what if I play not like a low note and a high note? What if I get rid of this one and I play two high notes? This guy here. Oh. Oh, interesting. It looks like two high notes being played next to each other. Can you see that the bottom ends up making kind of like a big arched packet almost? That's called a wave packet. And so you get like at the middle, this would be the loudness. At the ends, this would be the quietness. This is kind of zooming in on one of those beat packets that I was showing earlier, which is kind of why I wanted to show this one, is just to emphasize this idea of what the beat packet looks like. Like if I amp them up, I kind of make it a little bit more pronounced, okay? And I'm going to get rid of this one. Yeah, the other ones are still there. But see how I'm superimposing two different graphs on top of each other to get the bottom graph. Superposition is just adding stuff up. All right, let's get rid of that and come back over to the note. For the note, quickly just want to cap off with the idea of Mach. And Mach, I think we kind of already talked about this. We talked about supersonic jets and things like that. I actually I struggle with showing anything other than that simulator that we looked at earlier. Look, if I have an object in motion, we've already talked about Doppler effect, but this is the extreme. You guys asked for it earlier, right? When the object moves at the speed of sound, the wavefronts bunch up right here. So let's add on to that, okay? Little label, wavefronts stack on top of each other. Now that's when you're moving at the speed of sound. What that means is that those wavefronts, remember wavefronts represent high density regions, compression regions. And something about air is that air allows water to be dissolved in it. That's why we have humidity, right? And if I create a lot of air density all in one spot, all at one time, that's kind of like squeezing a sponge. If the air itself is the sponge that holds the water, if you squeeze the sponge, what happens to the water? Doesn't it get squeezed out of the sponge? So I want to add in that idea. When this happens instantaneously, condensation of water vapor occurs. You've squeezed the sponge. In this case, the sponge is the air itself. You've squeezed the water out of being dissolved in the atmosphere. Now, when that happens, the water vapor actually takes up more volume when it's a liquid than it was a gas, and it displaces the air particles around it when it gets squeezed out of the air. And displacing the air particles causes a shock wave. That displacement of the air particles sends a shock wave, which of course we call what? A sonic boom, okay? So I'm going to underline this, and I've left it for you as a little bit of reading because I feel like if I typed it, it would end up being communicated better than if I hand wrote it. But this sonic boom occurs when an object goes faster than the speed of sound. Now, it only happens when you go just crossing that threshold, because that's when these waves stack on top of each other, and that's when the water gets squeezed out of the atmosphere. So what's a sonic boom? It's the instantaneous water condensation. Sending a shock wave. When does it occur? We call that Mach 1. Okay, Mach 1 happens at the speed of sound. Okay, that's the only time it happens. You don't get it again when you hit Mach 2. Because when you hit Mach 2, the waves look like this, right? This is like the skipping stone we talked about earlier on, right? You don't cause the stacking of wavefronts when you go faster than the speed of sound, only when you just cross the threshold, okay? Now, people sometimes ask, don't pack up, we're going to finish. How do you calculate Mach number then? This is the easiest calculation ever. I would say even easier than beat calculations. Mach number is calculated just as a ratio. How fast is your object going compared to the speed of sound? Things that we talked about previously. If you're going faster than the speed of sound, you're going to create a sound cone where a plane that's going faster than the speed of sound, you won't hear it until it's already gone past you, right? So we've actually kind of precursor talked about this stuff as well. Supersonic jets, we don't hear them till they've already passed because you're standing right here by the time the sound gets to you. Okay? If we wanted to do a calculation on this one, it's just a ratio, so I'll leave you with that one. But at 0 degrees Celsius, the speed of sound is taken to be 332 meters per second. So we're going to use that value for what we're going to call a standard Mach. Okay? So the speed of sound is going to be 332 meters per second for when we calculate a standard Mach, because of course the speed of sound is temperature dependent, right? So of course there'd be all kinds of non-standard Machs. But what that also means is that when you're going at Mach 1, you might not quite hear the sonic boom right at Mach 1 because it might be a hot day. You know? Because we can call it a standard Mach, but that doesn't mean the sonic boom is going to happen at that speed unless you're flying on a 0 degrees Celsius day. Okay? And I'll leave that with you. Oh! Answer to this multiple choice question is B.
So you break it even if it's over 1?
Yep. Oh! Quick little thing about whips. You know that little crack of the whip? It's a tiny sonic boom. That's cute.